All right, everybody, welcome back. This is video 2 of section 3 of unit 4 of AP Calculus, rates of change in applied contexts other than motion. Last time we looked at some key ideas to have when we're working on these problems and did a few examples. We're going to charge forward and look at a bunch more examples in this video today. Hopefully I have enough time to get through all of the examples that I want to talk about. So let's start here with example 4 from the 2008 AP Calculus exam, free response number 2. We've got a table, time in hours, L of t measured in people. Concert tickets went on sale at noon, which is time 0, and were sold out within 9 hours. Okay. The number of people waiting in line to purchase tickets at time t is modeled by a twice differentiable function L. So L is the number of people. That means that L prime is going to be the rate of change of the number of people. Values of L of t at various times t are shown in the table above. First, use the data in the table to estimate the rate at which the number of people waiting in line was changing at 5:30 p.m. or time 5.5. Show the computations that lead to your answer. So we're looking for L prime of t, and we're looking for L prime of 5.5. So we want to estimate the slope, or estimate the derivative of this function, which we're going to use the average rate of change on the interval that contains time equals 5.5, and 5.5 is between 4 and 7. So I'm going to pick these 2 points right here in order to get our approximation. So I've got 150 minus 126 all over 7 minus 4. That's equal to 24 over 3. Or 8, and our measurement for that derivative is units of L of t, which is people, per units of t, so it's people per hour. So that is our estimate for the rate at which the number of people waiting in line was changing. It is increasing 8 people per hour. All right, let's go ahead and look at part C here of same question. What is the fewest number of times at which L prime of t must equal 0? Give a reason for your answer. Okay, so let's take a look back at this table. And remember that if we're looking for when L prime of t is 0, we're looking at the characteristics for L prime. Now, we know no matter what the behavior is between 0 and 1 here, we know that at least at one spot in that interval, L prime has to be positive. You know, it might be negative for most of the interval, but for at least some point in that interval, it has to be positive. It could be positive the whole time. It could be negative for a good chunk, but then positive one time. But we know that since L of 1 is bigger than L of 0, there has to be at least one place in there where L prime was positive. Same thing for 1 to 3. There has to be at least one place where it's positive. It might be positive the whole time. From 3 to 4, there has to be at least one place where it's negative. See how I'm finding these? We're just looking at, does L of t increase or decrease as time passes in my table? Here it increases again, and then it decreases, and then it decreases. Okay, so what does this information tell us? Well, the question asks us what is the fewest number of times at which L prime of t must equal 0. So we are assuming that this function is as well behaved as possible. In other words, when the derivative is positive in at least one point in an interval, then it's positive in the entire interval. And so we are looking at when the derivative changes sign, because when the derivative goes from positive to negative, since this is a continuous function, because it's differentiable, when the L prime of t goes from positive to negative, we're guaranteed that in the interim, for at least one point, L prime of t was equal to 0 by the intermediate value theorem. So let's see, we've got a sign change from positive to negative here, sign change from negative to positive here, sign change from positive to negative here, and so my answer is going to be there must be at least 3 times that L prime of t must equal 0 Okay. Every time we're guaranteed a sign change from positive to negative, or vice versa, from one interval to the next, the intermediate value theorem guarantees a zero value for L prime of t. I think that's a sufficient answer to that question. All right, continuing on. The rest of the examples we're going to look at in this lesson, we're going to look at problems that involve two rates, a rate in and a rate out, in order to determine whether a quantity is increasing or decreasing at a time or over an interval. We're going to compare the rate in and the rate out. If rate in is bigger than rate out, then the quantity is increasing. If rate out is bigger than rate in, then the quantity is decreasing. If those are zero, then the quantity is neither increasing or decreasing. It's actually probably easiest, and I say when doing these problems, it's frequently going to be easiest for us to create a third function, the rate in minus the rate out. And then if we find the rate in minus the rate out, if it's positive, that means it's increasing. If it's negative, that means it's decreasing. That's a little pointer on how you might want to approach some of these. So let's look at example 5 from the 2015 AP Calculus exam, free response number 1. The rate at which rainwater flows into a drain pipe is modeled by the function r. So the function r is the rate at which rainwater flows into. So that's the rate into. The pipe is partially blocked, allowing water to drain out of the other end of the pipe at a rate modeled by. So this is the rate at which water is draining out. But both of these are rate functions. So we're starting with the rate functions right off the bat. Is the amount of water in the pipe increasing or decreasing at time t equals 3 hours? Give a reason for your answer. So the rate of change of water in the pipe is equal to r of t minus d of t. If this is positive, then the amount of water in the pipe is increasing. If this is negative, then the amount of water in the pipe is decreasing. And we want to find this at time 3. So we're going to find r of 3 minus d of 3. And I'm going to go ahead and calculate what that is. So I'm going to break out my handy dandy calculator. If I can turn it on. Come on, calculator, wake up. There we go. All right, so I'm going to take r of 3, that's 20 sine of the quantity 3 squared over 35 minus d of t, so that's negative 0.04 times 3 cubed plus 0.4 times 3 squared plus 0.96, oh, missed my 9, 96 times 3, and this should give us the value that we want, negative 0.314, with negative 0.313 also acceptable if we truncate. Okay. Is the amount of water in the pipe increasing or decreasing? The amount of water in the pipe is increasing. Is decreasing because the rate that it is draining is larger than the rate that is flowing into, is larger than the rate that water is flowing into the pipe. Something along those lines. How exactly you explain that is up to you. All right, let's go on to example 6 from the 2007 AP Calculus exam free response number 2. Okay, so looking at this, we've got, let's see, the amount of water in a storage tank in gallons is modeled by a continuous function on the time interval from 0 to 7, where t is measured in hours. In this model, rates are given as follows. The rate at which water enters the tank is f of t, which we see in this graph right here. This is that curve. The rate at which water leaves the tank is g of t. It's these two horizontal lines. Okay, the graphs of f and g, which intersect at 1.617, that's right there, and at time 5.076 are shown in the figure above. Okay, so f of t is the rate at which it enters, g of t is the rate at which the water leaves. For 0 is less than or equal to t is less than or equal to 7, find the time intervals during which the amount of water in the tank is decreasing. So that happens when the rate at which water leaves is greater than the rate at which it enters. So from 0 to 1.617, you see g of t is higher than f of t. And also from 5.076 to 7, okay, and so for these, the amount of water is decreasing. Because the rate at which water is draining, the rate at which water is leaving, the rate at which water is leaving is greater than the rate at which water is entering. All right, takes us to the end of, did I read that wrong? I did. My God, that's terrible. My explanation is right, but my answer is wrong. This is the interval here from 3 to 5.07 where the rate it's leaving is, sorry, I just caught that at the very end. Oops. So instead of 5.076 to 7, this should be 3 to 5.076. All right, sorry about that. All right, I think that's where we're going to have to call it quits on this lesson for today. So we're going to come back next time. We've got a couple of more examples that we're going to look at, and then we'll be all finished with this lesson. All right, see you folks then. Have a great rest of your day, and enjoy yourself. Bye-bye.